Hello, good evening. So we'll start the session. I am delighted to welcome to IIT Madras Professor S.R. Srinivasawardhan, one of the towering figure of modern life. Born in 1940 in Chennai, then Madras, Vardhan took his bachelor's and master's degree in Chennai and earned his PhD in 1963 from the Indian Statistical Institute, Kolkata, under the guidance of Professor C.R. Rao. Soon after, he moved to the Courant Institute of Mathematical Sciences at New York University, a place that became his academic home for many decades. Vardhan is most celebrated for having developed a unified theory of large deviations. The work has had far-reaching influence, impacting fields as diverse as statistical mechanics, finance, population dynamics, and modern probabilistic analysis. Over his long career, he has earned almost every major honor in mathematics, most notably the Abel Prize in 2007, National Medal of Science from President Barack Obama, the highest honor bestowed by the United States government on scientists, engineers, and innovators, and also India's civilian honor Padma Vibhushan in 2023. So please join me in welcoming Professor S.R. Vardhan to deliver his public lecture. So I request Professor V.V. Rao to chair the session. Effects. Welcome to all of you at present said. As the rays of the sun are themselves an introduction of the sun. The words of Vardhan, introduction of Vardhan. So I request Mr. Vardhan to be his speaker. Be here today. Thanks. All issues with me to be guided to so I want to talk about large deviation. What is it? What exactly is it? Give some example of how it's developed and how it's seen. Can you hear me? Okay. So the method of large deviations was developed by the insurance industry in Scandinavia. They were worried about going bankrupt, as most companies are. So there are various reasons why you become bankrupt. Maybe you had too many claims. Maybe you had too many claims, or maybe large claims, and you may have reserve capital, and maybe the claims ate up your reserve capital, and now you're no longer able to pay your claims. So there are many, many reasons, and each one has a certain probability. So they wanted to calculate
What is the probability that the company survives for 1 year or 2 years, 10 years, or 10 years? How do you calculate these probabilities? And these probabilities are not significant. You can 0.50% chance of you're going bankrupt, you're not doing anything. Your probabilities must be very small. And like the equation theory deals with the problem for estimating these small probabilities. Not enough to say something is small. You have to know company survives for 1 year or 2 years, 10 years, or 10 years. How do you calculate these probabilities? And these probabilities are not significant. 0.50% chance of you're going bankrupt, you're not doing anything. Your probabilities will be very small. And like the efficient theory deals with the problem for estimating these small probabilities. It's not enough to say something is small. You have to know when it survives for 1 year, 2 years, 10 years, how do you calculate this probability? The best. Right? This best. Okay. Please. So with all that information and knowing the number of claims in the created per song, and its distribution, the sound distribution, the total claim is the sum of a random number of these random variables. So you can compute the exponential momentum. Yes. And it's a simple calculation, and you get a formula. So m theta is the exponential, the expectation of the exponential of a single random variable, and then you add these things, multiply, and you add the rate per some rates and some. So if you want to estimate the probability that this random sum is larger than nil, like the simple inequality that it's less than or equal to e to the minus theta times the expectation of e to the theta is, it is the end of this formula. So for any positive theta, you can estimate it like this. And then the left-hand side doesn't depend upon theta, and the right-hand side does. It behoves us to minimize the items. So minimizing the left-hand side is taking the soup of the exponential. Take the minus sign out, the e becomes a soup, and that's what you do. Usually, in practice, we take L to be the multiple of lambda. Because if you want to estimate the probability that your claims exceeds a certain amount, that should reflect also what the rate of the act. Now, there's a simple exercise one should do. The coin toss has probability P is A of coming up. And the probability that it comes up with 3 times n heads in thousands. You can compute it. And you can get a round for it using the Poisson bound. And it gives you this bound. The important thing about this bound is this function that you have, basically like entropy. So whenever you do large deviations, somehow the simplest example of binomial entropy. So the entropy is the entropy of two distributions. One distribution is binomial with probability P, the other one is binomial with C, and the entropy of the distribution with probability C with respect to the distribution of probability P. Statisticians call it. And e to the minus n times the entropy. Actually, in this case, you can check the estimate you have. Really a good estimate in the sense that the lower bound is not good. In quantum mechanics, systems prefer to stay the lowest energy. In the simplest case, the state of the system it can be viewed as a complex value function on the circle, which is called. And the energy in the system is sort of defined as the derivative of this plus a mean capital of V, some sort of potential to the average V. Energy. So you want to minimize the energy over all functions. You have to know what the state of the system is given by it, and you minimize the energy. This is to account with the radiation problem. I use a certain differential equation, and lambda is the Lagrange multiplier. This is the radiation equation. This is, of course, an eigenvalue problem. You see the eigenvalues, the countable number, and the minimum corresponds to the with respect to the equation can be the integral b with respect to probability density b. Of course, if g is not 1, this probability is very small. So most of the probability is concentrated at g equals 1, but for g not equal to 1, there is some probability the exponential decay, what is then you have a bunch of growing exponentials. What matters contributes to introduce the largest value. The largest value means you want to choose the G with the smallest I. The smaller the I, the the faster this grows. So if you look at the weighted sum and you calculate some simple analysis, the basic idea here is if we have a bunch of exponentials and you add them with positive weights, the fastest growing exponential overtakes everybody else. So your lambda naught should be the supremum of various contributions. And because of the change of sign, you can write it in this manner. So what matters is the minimizer G. But the minimizer G, if you look at the variation formula, it's clear we have already another variation formula, which is the minimizer of the calculus of variation problem that we started out with was minimizer of integral V phi square minus P prime square. So you can't have two different variation formulas of the same thing. Can't be a coincidence, right? So they should be the same thing. So the minimizer of G here should be the square of the eigenfunction. So del tells you that I of G, you can guess it to be this quantity. What this is just the Dirichlet integral phi prime square, or phi is square root of that. So in terms of the density, this is the large deviation. The large deviation here is deviation from the ergodic theorem of Brownian motion. So the largest exponential dominates lambda naught. This this is the rate of large deviation probability dk given by this form. And the relation between G and F is G is just F squared. So here is another example of large deviations. Suppose you have a simple random walk on the d-dimensional lattice. Let Kn be the number of distinct cycles in the first n steps. So if you visit the same site twice, it counts only once. So you just count the number of sites visited. Certain sites are radioactive, and the walk survives only if it avoids these traps. So you want to calculate the probability. Well, the probability that the site is trapped is some probability P, you write it as E P minus C. So that's the probability that a site is not a trap. So 1 minus E P minus C is the probability that it's a trap. Anyway, it's just a way of representing any P as 1 minus E P minus something. And it's independent for different sites. So e to the minus c times kl is the survival probability in steps. Because you have to in steps, if you visit so many sites, you must survive each one. So you want to estimate expected value of e to the minus c times. One can easily compute the expected number of visits you need. Oh, blank page. So the next. Now, in one dimension, the problem is trivial because the random walk doesn't miss any, there's no gaps. So it's just the range of the random walk. So it's the max minus the min, and you can compute its distribution. Whatever. The range of the random walk is what? Is the number of visited sites. And if you compute for n equals 1, it's square root of that. Now, of course, the number of sites you visit can be much less. And if it's much less, your survival probability is more. So if you want to survive, it's probably better not to go too far. So you have to compute the probability that the random walk doesn't go too far and balance it against the survival probability. And there is a little variation here to little optimization problem you need to do. And if you do it, you get the number of the sizes n to the alpha, the probability is n over n to the 2. See, the probability of surviving, probability, you could think of it, what is the probability that a random walk is confined to a certain region? And if the region is small enough, Gaussian approximation is good. And it could the same as what's the probability that Brownian motion is contained. And you can work, depends on the dimension. In terms of the radius of the circle, it's just time divided e to the minus the time divided by the constant times the square of the radius. And it's very well worked out. And if you work it out and you do the calculation, there's a fight between alpha and 1 minus 2 alpha, because alpha is the decay rate of the probability, 1 minus 2 alpha is staying within the radius. And you optimize it, you get 1/3 in dimension 1. So survival rate is e minus the constant times n to the 1/3. Slightly more involved argument gives you that it's e minus the constant times n to the d over d plus 2. The explanation for that is that you limit the ball to so the radius are dictating something in my hearing aid which I don't want. If you limit the walk to remainder of ball radius r, the sites visited is of order r to the d. Because that's how many sites there are roughly. And the probability is e to the minus n over r squared. And if you balance one against it, I'm not, there are constants everywhere floating around. I will bother to write them down. You get n to the d over d plus 2. Well, you can look at random graphs. That does any graphs. The number of possible edges is n choose 2. Each edge is either there or not there. It's there with probability p, and not there with probability 1 minus p. They're mutually independent. And the expected number of edges is n choose 2 times p squared. And the expected number of triangles is n choose 3 times p cubed. If for some t larger than p cubed, we condition the random graph to have t times n choose 3 triangles, how many edges would it have? I'm going to remove my hearing aid because somebody is trying to talk to me. Some advertisement. Buy this, sell this. So if for some t bigger than p cube, we condition the random graph to have more triangles. How many edges would it have? Now, how did these more triangles appear? Would it be because you had just had more edges? Or is there some other reason how, with fewer edges, you can manage to get more triangles? Well, there is a way you can form clusters. Well, the increase in triangle, is it due to clustering or is it due to large number? How do you resolve it? You have to calculate certain conditional probabilities and analyze what happens to this. So that's where large deviation comes up. So just we calculated before the probability distribution of the number of hits, the probability for excessive number of hits. That was the entropy calculation we did in ADR. But think of the number of vertices is becoming large. These are asymptotic things. So that means you can think of the number of vertices being, the vertices being continuum in the interval 0 to 1. So think of f of xy as a local proportion of edges that connect between x and y. It's not quite between x and y, but a little tiny neighborhood around x, a tiny neighborhood around y. How many edges are there? Think of it as f. Then your distribution of edges, if it's not uniform, the probability that it's something else is like that. And then you can calculate in terms of f, how many triangles you have, how many graphs of, how many finite graphs of a given shape you have. And then if you want to compute the probability of that, it will decay exponentially in n squared now, because the randomness is of size n squared. And you have to minimize this entropy because all the things are happening simultaneously, and the one that dominate will be the one with the least entropy. You can think of the entropy as creating something bad, but the cost of creating it is the entropy. So you want to have some effect, you want to have it with the least cost. So this is the proportion of triangles. Because the triangle means connect x1, x2, x3. So you want to fix f to be this, and you want to minimize this. That tells you the story. So the question really is the minimization attained at a constant f, or is there a non-constant f which does better? And you can prove that for t close to p cube, constant is best. But if you move away, then constant is not the best. So there's a phase transition when you increase the value of t. And can form cliques, and then it's better. Then there are Gibbs states. In statistical mechanics, you can describe a system by expressing its density. So here, L is the size of the system. It could be a block, d-dimensional block of size L, and you specify a probability density. Well, I think we saw this before earlier today. By sort of this moving window, some local finite function, and depending on a finite number of variables. So I'm being very general here. This could be any kind of local function. And you look at the exponential of that, and you normalize it by the expectation so that you have a probability distribution. And you want to know here is a question for which you're looking for an answer. You have a probability density of x, and you have dp, and you want to estimate the probability that under this fx dp, what is the probability for A? You expect it to be small, and you want to know how small it is. Now, I don't like F because it gives me a very small value. I like G better because under G, the probability is at least 1/2. So I'm going to pretend that the actual density is G and not F. I can cheat by writing F as G times e to the minus log of G over F. It is just if you compute, that's just using F. So now I can use Jensen's inequality and get a lower bound in terms of the expectation of log G over T. So that's the entropy bound. So the cost of entropy, you can change your distribution, and by magic, something with small probability becomes a significant probability. And then how small the original probability is in terms of the entropy of one system to the other. So you get this Jensen's inequality, and you tilt from FTP to GTP. And this tilting is used, for example, in statistics, important sampling. And it's a useful way of estimating small probabilities. But lower bounds you get here. For upper bounds, we already saw the generating functions. There were ways of getting upper bounds. And if here, of course, G is up to you. G is not unique. There are various G's. And if you are lucky, you hit on the right G so that both the bounds, upper bounds and the lower bounds, are fairly close. So the cost here is that entropy is the cost. And these ideas go back a long time. Feynman uses such ideas to do certain things. So you pair with entropy and minimize the cost. I think I've done. The trouble with slides is they go fast. Thank you. I hope I conveyed some idea of what large degrees can do. There are various other applications. For instance, there are systems in which, think of this, you have particles, large number of particles that move around, and you want to know, if you measure the density, then for the density, there should be an equation to sort of evolution of the density, which is a partial differential equation. You start with a system of stochastic process, which each particle does, and then you want to end up with this. And that depends on how many particles you have, and for the system of equations, what are the invariant measures, so that locally the system will be in equilibrium, but different equilibrium at different points, because the equilibrium depends on how many particles you have. So there is a kind of a combination of probability, large deviations, and differential equations. You have to use the whole mix in order to. So large deviations occurs in many places. Hope I've given you some idea of what one can do. Thank you. Open for questions.
Anybody would like to? What's the unified? You mentioned some unified class division. What's the unified? What was the unifying thing? Like earlier it was not unified. Yeah.
There's no, there should be a switch where it's turn on. Can we have one more? Yeah. Somebody is calling, making phone calls.
Yeah, the question is,
Okay,
yeah, the question is what is the unifying factor in large deviations? Right? Yeah.
what is the question? The question, unification comes from entropy. For instance, in statistical mechanics, there's something called partition function and free energy. And what it is, we saw that you have exponential of a sum, and you want to compute the expected value of that, and take the log and divide by the volume and take the limit. And that's really, you want to know how fast these things grow. And the moving average, it should be the expectation to be something else. But there's a large deviation there. That's really the entropy controlled by entropy. So there is energy, there is entropy. And the free energy is just the balance between these. So in some sense, entropy controls everything. And also, there are various principles. If you have two different systems, which are not linear with each other, entropy just adds up. And if you have a subsystem, you have a bigger system, and if you want to compute large deviation here, it's just entropy there, and we minimize the entropy, given the conditions below, that's the rate function for the large deviations here. So entropy is sort of an umbrella way on top. Everything you can think of comes from it.
I have just one question.
Go ahead.
So it is believable that whenever the sequence converges to stochastic value. So it is believable that whenever something converges, it probably converges at an exponential rate in probability. But however, in the large deviation theory, there seems to be a global rate function, right? Why is there a global rate function? To make it more precise, the averages of IIT random variables converge to. So you can get some exponential inequality converting to mean. But however, there is a global rate function in the large deviation field, right? On the entire space. What makes it happen?
See, when the mean changes, that's because your sampling distribution changes. So if you knew the large deviation for sampling distribution, you can derive from it the log deviation rate function for the mean. So you can go one step above. When you go one step above, you get Kullback library information. And you can go even one step further than that, because sampling distribution could be sampling distribution of blocks. So you get the entropy of one stochastic process with respect to another. That's what comes up in partition functions in statistical mechanics. So in some sense, there's a grand large deviation involving nothing but entropy. Entropy rules. And then everything else is a descendant of entropy.
Terms of the rate function, it captures the rate at which things decay with respect to the first order. If we look at maybe things which are corrections, like after we remove the first order, we are looking at perhaps other corrections. Are there similar rate function like quantities that come in which apply for the corrections, and is there any interpretation if there are any corrections? So e to the minus n, maybe the next order term is something smaller. Are there constants that we can?
It depends. Now, in the best situation, the exponential has only a constant correction. And that constant can be avoided. What it requires is that you do some three-dimensional differential geometry. When you have a calculus variation, you have a minimum. At that point, the gradient is zero. And the Hessian is the correct sign. And that Hessian is eigenvalue. The eigenvalue has determinant. And that determinant is a constant. Two within multiples of pi or other. So in some sense, in the nice situation, or the expansion allows the sampling of the entire world, you can get the constant. There are other places, other orders, where you don't have that control.
physics problems you work on, or for instance, the motion of the photon. How did you come across these problems and how did you realize that they fall under the umbrella of classification again?
Um, Whenever you have a large system and you want to do something with it, unless it's a simple calculation or you want to compute some expectation with respect to this system, there's usually large deviation involved because you have a distribution and what you want is something else, right? The all-around problem has a statistical mechanical thing, and you want to compute the partition function, and you want to compute with the asymptotics in the partition function. That's very much large deviation.
There are no more questions. Yeah, wait. One more.
Could you narrate the story of how you found out the eigenvalue, eigenvector connection? What prompted you to look in that direction and connect it to large deviations?
Early on, there are various kinds of large deviations. For example, one can ask, if you have a Brownian motion, the small time it doesn't go very far. Suppose I had a Brownian path which happened to go very far in a short time. What path did it take? As a theorem of Stochastic, it says it went straight, by a straight line. So the question then is, what if it's not flat space, but some Riemannian space with some metric on it? And Brownian motion, there is Laplace in that metric. And so you have a path which are Brownian in that sense. Then how did it go? The best guess is it went according to geodesy. So that's our case.
Okay. If there are no further questions, let us thank question further.
Thank you very much coming to IIT Madras and coming and giving us in a very short notice, giving a public lecture. And we thank you on behalf of IIT Madras as well as LPS organizers.
Thank you.